Hello everybody. So, for today's video we're going to be talking about the fundamental theorem of line integrals. So we talked about line integrals a little bit last time. There are, when you are integrating over a particular path or a line instead of over a full region. I've already talked about where these can be important, but there's some other aspects of these which we're going to see in this video, which is why line integrals are actually fairly useful and they are convenient because of some of the things we're going to see here. So let's go ahead and jump right in. First of all, the fundamental theorem itself. Let C be a smooth curve given by the vector r of t, and t goes from a to b. Let f be a continuous function of n variables, so number of variables doesn't really matter, whose gradient of f is continuous on C. So you need the function itself to be continuous and its gradient to be continuous. Then the line integral just comes out to your function evaluated at the endpoint of the vector minus the function evaluated at the beginning of the vector. That's all that happens. Now, this should seem similar to the fundamental theorem integrals in general or integration calculus. They're all fairly similar. They follow the same basic logic. There's a reason why they're all called the fundamental theorem. They're all derived from the same thing. Alright. So what are some of the aspects of this that we get from this theorem? So, a couple of implications. Regardless of what curve you are following and what vector function you're using to get there, if your gradient is continuous, and the paths have the same start and end spot, the integrals can come out to the exact same thing. Pretty easy for that part. So if you realize some other path is going to give you a much simpler formulation, go with it. And it's not going to change anything for you. Now, another thing, if it is a closed path and your gradient is continuous, then the integral is 0. So if by closed path, that means if you're forming some sort of enclosed shape. So it could be a circle, ellipse, some really weird stuff. Regardless of what it is, if delta f is continuous, then it's going to come out to 0. Now, there are a few other theorems that go along with the fundamental theorem and come from it. So let's take a look at a few of them. So, if the line integrals are independent of path in your region D, if and only if it comes out to 0 for every closed path in your region. So that kind of comes from the previous implication we've talked about. So you have to keep in mind, if it comes out to 0 for every closed path, then it's independent of path. Now, if it does not come out to 0 for every closed path, that means there are going to be some places where that's not true. Now note, f is no longer required to be continuous for this. Quite often though, it'll be a case that if f is not continuous, well guess what? That's where your issue occurs. Now keep in mind, f is bolded, so it's a vector. Now, suppose f is a vector field that is continuous on an open connected region D. So, open. Basically, you're not including the boundary. Connected. That means you're not going to have multiple places for where this exists. It's all one big shape. Now, if your line integral is independent of path in D, then f is a conservative vector field on D, which essentially means f is a gradient of something. And you potentially could find what it is. Okay? Now, this one's going to be fairly important, especially later on. So if you can write f as a function of 2 variables for I, and then a function of 2 variables for j, on an open, simply connected region D. So simply connected quite often means there's not going to be any holes within it either. And suppose P and Q have continuous first order partial derivatives. Alright? then f is a conservative if and only if the partial of p with respect to y is equal to the partial of q with respect to x for the entire region. So this is going to be very important later on when we discuss some of the theorems later in the chapter. But just keep in mind you have an if and only if here. So if you can show one of these, you get the other for free. Now, all right. See you in class.